Hello, today we're going to talk about section 9.9, and this is all about relating cell potential to free energy. Okay, so remember that when you're looking at the overall cell potential, you need to first look at the reduction potentials for the two half cells. You'll have an oxidation half cell and a reduction half cell, but they always give the reduction potentials. So let's say, for example, I have two half cells and their reduction potentials are, let's say, 0.5 and negative 0.3. Whichever one is smaller is your oxidation half reaction, and whichever one is larger will be your reduction half reaction for a voltaic cell or a galvanic cell. And that's because the voltage for a voltaic cell has to be positive. So to calculate then the overall cell potential, you will take the reduction potential for the reduction half reaction, which is 0.5 in this case. And then you're going to add the reduction potential for the other cell, but you have to flip the sign because the reaction is going to flip. So from reactants to products, you're going to flip that around, products to reactants. And when that happens, you change the sign of this reduction potential. So we will change this to a positive 0.3. So that means my cell potential for the overall reaction is 0.8, which is a positive value, which works for voltaic cells. Now, this indicates that the reaction is thermodynamically favorable. It's spontaneous in the forward direction. This makes sense because voltaic cells or galvanic cells don't have a power source. You just hook them up and the reaction just happens. Okay? So that means that delta G for this must be a negative value. If you were to look at your cell potentials for a particular setup and you'd wind up with a negative cell potential, then that must be an electrolytic cell. Electrolytic cells, you have to have a power source. When there's a power source, that is not a spontaneous reaction. You're putting in work from the power source, so delta G will be positive. Now, you can relate the two together using this equation. Delta G at standard conditions is equal to negative NFE, where delta G is your Gibbs free energy. N is the moles of electrons that are being transferred in that process. F is Faraday's constant, which is on your formula sheet. It is 96,485, and the unit for that is coulombs per mole of electrons. And then E, at standard conditions, is your overall cell potential. So you can convert between cell potential and free energy using this equation, and notice that you have the negative sign here. So when you have a positive cell potential, you have a negative delta G. When you have a negative cell potential, you wind up with a positive delta G. Okay, so here's an example with gold and silver, and the overall cell potential for this whole reaction is 0.7 volts. If I want to calculate delta G, I can use the equation delta G equals negative NFE. Delta G, so the number of moles of electrons, I need to look at that because the gold is going from a +3 charge to a 0 charge. You can just focus on one atom for this, or if they give you more information, you can look at the actual process itself. So there are 3 electrons that must be transferred there because the gold is going from +3 down to 0. So I know that there's 3 moles of electrons happening in that process. Faraday's constant, 96,485. And our cell potential they gave us is positive 0.7. Now it's a positive cell potential, so I know delta G is going to be negative. It's spontaneous, it's thermodynamically favorable, but the actual value that you get is 2.0 times 10 to the 5th joules per mole, but again, we usually read that in kilojoules, so that would be, I'm sorry, that's negative 2.0, my bad. So in kilojoules, that would be negative 2.0 times 10 to the 3rd kilojoules per mole. So here's another example. We have the following standard reduction potentials for those two half reactions. We want a thermodynamically favorable reaction, so that means delta G must be negative, and that means our cell potential must be positive. So that's what it means it's a voltaic cell, because it has a positive voltage. It must not have a power source. So if we write the reaction for a voltaic cell, we want to take the smaller one and flip that reaction around. So we'll get H2S yields S plus 2H plus 2 electrons. And our cell potential for this is negative 0.12. Now, if you add the two reactions together at this point, you would get the chlorine gas plus the H2S will leave us with solid sulfur, 2 hydrogen ions, and the 2 chloride ions. The electrons cancel. There's 2 electrons in each, which is great. And then to find the cell potential in volts, you would add together this negative 0.12 because we flipped it, and the positive 1.36, and you get that the cell potential is a 1.24 volts. Now for C, it's asking how many moles of electrons were transferred. Well, that's easy. There's 2. You can just look at the process there. If you had to multiply one of those reactions to get them equal, make sure you use the number of electrons that makes them equal for both reactions. So that's 2 electrons there, and calculate the value for delta G. We need to use delta G equals negative NFE. And so if we plug in, there's 2 moles of electrons, Faraday's constant, and our cell potential we found was 1.24. When you multiply those, you get a negative 239,000 joules per mole. But let's put that in kilojoules. So negative 239 kilojoules per mole is my delta G.